Louis Vuitton does not approach manufacturing as a race for speed. It approaches it as a controlled system of permanence. Every product begins not as an object, but as a decision. A decision that this item must outlast trends, usage cycles, and time itself. The factory is therefore not optimized for maximum throughput. It is optimized for consistency, traceability, and mastery. The manufacturing philosophy is built on a hybrid model. Human craftsmanship remains central, but it is reinforced by industrial precision. Machines do not replace artisans. They stabilize outcomes. Technology exists to protect quality, not to accelerate volume. This balance defines how Louis Vuitton operates across its global manufacturing network. Production begins with material selection. Leather is not treated as a commodity input. Each hide is inspected individually under controlled lighting. Texture, elasticity, grain density, and natural markings are evaluated by trained specialists. Defects that might be acceptable in mass-market production are immediately rejected. The goal is not uniformity through processing, but uniformity through selection. Once approved, leather moves into preparation zones. Here, temperature and humidity are regulated to prevent material stress before cutting. Digital pattern systems guide placement to minimize waste, but final positioning decisions are still validated by human eyes. This stage ensures that structural integrity is preserved before assembly even begins. Cutting combines automation and manual control. Precision cutting machines execute pattern geometry with millimeter accuracy. However, the feed rate, pressure, and alignment are constantly monitored by operators. This prevents microfractures in the leather that could compromise longevity. In areas where curves or structural transitions occur, cutting is often completed by hand to maintain tactile feedback. Assembly does not resemble a traditional factory line. Instead of a single bag moving through dozens of stations, work is grouped into cells. Each cell is responsible for a defined structural section of the product. This reduces cumulative error and ensures accountability. If a flaw appears, its origin can be traced immediately. Stitching is one of the most tightly controlled operations. Machines are calibrated daily, sometimes multiple times per shift. Thread tension, needle penetration depth, and stitch density are verified against internal standards. Operators are trained to detect vibration changes in the machine, signals that something is deviating before it becomes visible. Critical seams are reinforced using multipass stitching patterns. This is not done for aesthetics. It is done to ensure load-bearing durability under long-term use. Handles, corners, and stress points receive additional attention, often involving manual adjustments after machine stitching is complete. Edge finishing is where luxury becomes measurable. Raw leather edges are sealed using layered applications of paint and heat. Each layer must cure before the next is applied. This process can take days, not minutes. Rushing it would reduce resistance to moisture and abrasion. The result is an edge that maintains integrity after years of handling. Hardware integration introduces another layer of precision. Metal components are manufactured separately, often by specialized suppliers, then finished and inspected internally. Polishing removes micro-imperfections that could accelerate corrosion. Engraving ensures traceability and brand authentication. When hardware is attached, torque values are controlled. Too loose compromises stability. Too tight damages leather fibers. These tolerances are not estimated, they are measured. This is where engineering discipline intersects with craftsmanship. Internal structures are assembled next. Linings are not decorative additions. They are structural elements. Alignment ensures that stress is distributed evenly throughout the product. Symmetry is verified visually and mechanically. If imbalance is detected, the product is disassembled and corrected rather than adjusted cosmetically. Throughout assembly, inspection is continuous. Quality control is not a final gate. It is embedded into every stage. Artisans are trained to self-inspect before passing work forward. This reduces downstream corrections and maintains production integrity. The manufacturing environment itself is part of the system. Lighting is neutral to avoid color distortion. Noise levels are controlled to prevent fatigue. Workflow distances are minimized to reduce handling damage. Even movement patterns inside the factory are engineered to protect materials. What emerges from this process is not just a finished product. It is a controlled outcome of thousands of decisions, each designed to reduce variability and increase lifespan. Speed is deliberately sacrificed. Volume is deliberately constrained. The factory operates with the assumption that every item will be examined closely, by inspectors, by customers, and by time. This is the foundation of Louis Vuitton manufacturing. Not scale alone, not craftsmanship alone, but a disciplined system where tradition is stabilized by engineering, and luxury is treated as a measurable standard rather than an abstract concept. If you want to continue inside how these products are tested, validated, and certified before reaching the world, like this documentary. Once assembly is complete, a Louis Vuitton product does not move forward by default. It enters a validation phase designed to answer a single question. Can this object survive long-term real-world use without structural compromise? Luxury in this system is not assumed. It is proven. Testing begins with structural verification. Every load-bearing component is examined under controlled stress conditions. Handles are subjected to repeated pull cycles that simulate years of carrying weight. The force applied is not arbitrary. It is calculated using historical usage data and safety margins. If deformation exceeds tolerance, the product is rejected regardless of visual perfection. Seams undergo tension and flex testing. Stitch density alone is not enough. Engineers evaluate how thread interacts with leather fibers over time. Microscopic inspections are used to detect early signs of tearing or separation. These tests are designed to expose failure before it reaches the customer. Abrasion resistance is measured using rotating contact systems that simulate continuous friction. Corners, edges, and high-touch surfaces are tested first. These are the zones where wear appears earliest in real use. The goal is not to eliminate wear entirely, but to ensure it develops uniformly and predictably rather than catastrophically. Environmental testing introduces controlled stress from outside factors. Products are placed in humidity chambers that cycle through extreme moisture conditions. Leather expansion and contraction are measured to ensure seams remain stable. Temperature variation tests expose materials to heat and cold transitions to verify adhesive integrity and surface finish durability. Color stability is verified under ultraviolet exposure. This ensures that pigments do not fade or discolor under prolonged light. Each material batch is compared against reference standards. Even minor deviations are flagged. Consistency across time matters as much as consistency across products. Hardware components undergo separate validation. Clasps, locks, and fasteners are tested for repeated actuation cycles. Opening and closing mechanisms are measured against resistance curves to ensure smooth operation without loosening. Corrosion resistance is evaluated to prevent degradation from environmental exposure. Beyond physical testing, traceability systems operate continuously. Every product carries a unique identifier linked to its material sources, production cell, assembly timeline, and inspection history. This allows any anomaly discovered later to be traced back to its origin with precision. Anti-counterfeit measures are embedded at this stage. Micro-engraving, material signatures, and digital authentication markers are integrated into components. These features are designed to be invisible during normal use but verifiable through internal systems. Protection of brand integrity is treated as part of product engineering, not marketing. Certification is not a single approval step. It is cumulative. Each testing phase generates data that must align with internal benchmarks before progression is allowed. If any metric falls outside tolerance, the product is either reworked or removed entirely from circulation. Inspection teams operate independently from assembly. This separation ensures objectivity. Inspectors are trained to detect not only defects, but deviations from brand standards. Texture feel, symmetry, and tactile response are evaluated alongside mechanical data. Digital systems support this process through analytics dashboards. Aggregated test results reveal trends over time. If a specific component begins to show marginal performance, production parameters are adjusted proactively. This feedback loop prevents systemic drift before it becomes visible externally. Only after passing all validation stages does a product receive final release authorization. Packaging does not occur until certification is complete. This ensures that every item entering the supply chain has already proven its durability, stability, and authenticity. At this point, the product is no longer considered a prototype or a manufactured object. It is considered a verified unit within a controlled ecosystem. It is ready to interact with the world, but the system does not stop observing it. If you want to see how these products perform in real-world use, how data flows back into the factory, and how future generations are shaped, subscribe to continue the documentary. Once a Louis Vuitton product leaves the factory, manufacturing does not truly end. It transitions into a monitoring phase. The object enters the real world, but it remains part of an extended system designed to learn from use, environment, and time. This phase is where craftsmanship meets data and where future design decisions are shaped. Products distributed globally are tracked through serialized identification systems. While customer privacy is maintained, performance trends are observed through repair data, warranty evaluations, and service interactions. These signals provide insight into how materials behave after prolonged exposure to daily life, travel, climate variation, and handling frequency. Louis Vuitton maintains internal repair and refurbishment networks. These are not external afterthoughts. They are integrated into the manufacturing intelligence loop. When a product returns for servicing, technicians document wear patterns, stress points, and material response. This information is logged, categorized, and analyzed. Certain areas consistently reveal critical information. Handle curvature changes indicate load distribution accuracy. Edge paint degradation reveals environmental exposure thresholds. Stitch fatigue exposes cumulative motion patterns. These observations are not treated as failures. They are treated as performance data. This real-world feedback informs material evolution. Leather tanning specifications are adjusted. Thread composition is refined. Adhesive formulations are modified to improve flexibility without sacrificing strength. Each change is incremental, controlled, and tested before deployment. Design evolution follows a similar discipline. Structural reinforcements are repositioned based on stress mapping. Internal linings are modified to improve shape retention. Hardware tolerances are recalibrated to balance smooth operation with long-term stability. These changes are rarely visible to the consumer, but they define product longevity. Digital modeling plays a growing role. Data from physical products feeds simulation environments where accelerated life cycles are tested virtually. This allows future designs to be stress-tested before physical prototypes exist. However, digital validation never replaces physical testing. It only guides it. Sustainability is increasingly integrated into this phase. Lifecycle analysis identifies where environmental impact can be reduced without compromising durability. Material sourcing is evaluated for long-term availability. Energy consumption within factories is optimized based on production data. Waste streams are redesigned into closed-loop systems wherever possible. The human element remains constant. Artisan training evolves alongside tools and data. Skills are documented, preserved, and transferred to ensure continuity. Automation supports consistency, but final judgment remains human. This is deliberate. Luxury manufacturing depends on discernment as much as precision. Future factories are designed around this philosophy. They are quieter, more data-driven, and more modular. Production cells adapt faster to design updates. Inspection systems become predictive rather than reactive. Yet the core principle remains unchanged. Durability over speed, traceability over volume, trust over spectacle. Louis Vuitton's manufacturing system does not chase novelty for its own sake. It refines, it stabilizes, it listens. Each product becomes part of a long feedback cycle that stretches across years and generations. What the customer carries is not just a finished item, but the current expression of a continuously learning system. In this model, luxury is not defined by exclusivity alone. It is defined by reliability, accountability, and time. The factory does not disappear once the product is sold. It remains present, embedded in every seam, every edge, and every decision that shaped the object. This is how Louis Vuitton manufactures products, not as isolated artifacts, but as enduring systems designed to perform, adapt, and last. If you've watched this entire journey, share your perspective, comment below.